Okay, we retain another integral. This one's from the Berkeley Math Tournament 2015, tiebreaker number 2. We have the integral from -1 to 1 of x squared over 1 plus 2015 to the x dx. Okay, this is actually a pretty common problem that comes up in integration bees, and it's very specific where we have bounds symmetric around 0. We have an even function here in the numerator. We have 1 plus a constant and an odd function on the exponent. So it really has to all line up. But what I want to do on this is actually use King's principle. I'm just going to put some labels on the bounds. We'll say this is our lower bounds A, our upper bounds B. And for King's principle, what we want to find, if this right here, we'll call this f of x, then for King's principle, we want to know what is f of b plus a minus x. And specifically in our case, it's pretty nice because when you add b plus a, that's just 0. So what we really want is just f of minus x. So when we use King's principle on it, the bounds stay the same, and we're just going to transform everything to f of minus x. So when we do that, we have minus x squared over 1 plus 2015 to the minus x dx. But now here in the numerator, if we're squaring something with a negative sign, the negative sign just goes away. That's not going to matter. But now one thing I want to do is, I'm thinking I want to add this back to what we have here of our original integral. Let's kind of put some labels on it. We'll call our original integral I. We'll call this one I. But before we try to add anything up, what I want is the same denominator. And the trouble is here in the exponent, we've got this minus sign, so it's not quite going to work. But now what I can try to do to fix this is let's multiply in by 1. Just multiplying 2015x. So when we distribute this in, let's see how it goes. We end up here, same bounds. The numerator becomes x squared 2015 to the x. Then let me just reorder it. So when I multiply 2015x times 2015 to the minus x, the exponent becomes 0. 2015 to the 0 becomes 1. Then I multiply this by 1, and we get just 2015 to the x. And now we got the same denominator. So again, this here is I. So let's just take this copy right here and add it to our original. When we do that, if we have two copies, we have 2i. Both these have the same bounds, same denominator, so we'll just copy that over. But now when I add the numerators, we have x squared in common. So let's factor out x squared in front. We have like a 1 coefficient we can kind of create right there. And so this is going to be 1 plus 2015 to the x dx. And this is where the real payoff happens, because then we can just cancel this with this, and now we're just integrating x squared. And now for just an optional step, because we have an even function here and bounds symmetric around 0, I can take this and just update the lower bound to 0 and then bring a 2 up front. And then actually while I have it, let's isolate, we want to solve, our goal is I, so let's divide off a 2 on both sides. So now we're just going for I. So now we just have an I on the left side, 2's cancel here, and we have an easy integral. So going ahead with this, we'll integrate just using power rule. We get x cubed over 3, just evaluate it from 0 to 1. At 0, this is nothing, plug in 1, and so for my final solution of this, we just get 1 over 3. And again, we could have done this quicker, just recognizing the form that I mentioned initially with this perfect setup. Then what happens is this part goes away and we just end up integrating this x squared. So when you get used to seeing these and you recognize that you can actually kind of skip everything and just go to a really easy integral. Hopefully the even function on the numerator is an easy thing to integrate, and then you basically go right to the solution. Okay, there you have it. Good one from Berkeley Math Tournament 2015. Thanks everyone for watching. Have a good day.